Hello, everyone, and welcome to this IEEE SIGHT webinar. We're very happy to have you join today's session, which will be on leveraging semiconductor technology for the benefit of society. For those of you who may not know, IEEE SIGHT is a subcommittee of the IEEE Humanitarian Activities Committee. And SIGHT is a global network of volunteers that partner with underserved communities and local organizations to leverage technology for sustainable development. At present, SIGHT has over 7,500 members and 150 groups that are working in communities all around the world to accomplish and further this mission. And today I am very excited and happy to be able to introduce the SIGHT Education Subcommittee Chair, Dr. Fernando Guarin, who is an IEEE Fellow and a distinguished member of the technical staff at Global Foundries in New York. At Global Foundries, Dr. Guarin leads the reliability team responsible for the qualification of 5G technologies. So Fernando earned his BSEE from the Pontificia Universidad Javeriana in Colombia. He has also earned his MSEE degree from the University of Arizona and his PhD in electrical engineering from Columbia University in New York. He has been actively working in microelectronic reliability for over 35 years. So he is extremely well qualified to speak to us today on this topic. Dr. Guarin is an IEEE Fellow. He is a distinguished lecturer for the IEEE Electron Devices Society, or EDS, where he has served in many capacities, including a member of the EDS Board of Governors, a chair of the EDS Education Committee, secretary for EDS, and then from 2018 to 2019, he also served as the IEEE EDS president. So I'm very happy to have him here today sharing on this SIGHT webinar. Again, that will be leveraging semiconductor technology for the benefit of society. And so now I'll go ahead and hand it over to Fernando. Thank you so much for being with us today.
Excellent. Thank you so very much, Juliana, and a good day to everyone. I hope that everybody is healthy and safe in these challenging times. And this is the first of a series of webinars that we're sponsoring through the Special Interest Group in Humanitarian Technology SIGHT. So we'll be sharing next week for anybody that's interested. We will be redoing this in Spanish. So we'll have a repeat. So I think Juliana went pretty much through our vision and mission for SIGHT. So it's basically to work with underserved communities throughout the world and make sure they can benefit from technology. And so it's really a network of volunteers from around the globe that we partner with underserved communities and local organizations to leverage technology for sustainable development. So today's talk, as Juliana indicated, is to take a look and see how we can leverage technology. And it's also co-sponsored through the Electron Devices Society, which the motto is to promote excellence in the field of electron devices for the benefit of humanity. So as Juliana indicated, we have a little over 10,000 volunteers distributed throughout the globe. And you can see in this map the many site groups that are currently active. So it's a pleasure to be here. So I'd like to start this talk and have you just spend a few seconds to think about what your life would be like, you know, if you did not have your cell phone, your laptop, no technology whatsoever. We can all picture ourselves by some beautiful beach or some other idyllic place in the world. You know, and lately we've had a respite somewhat from normal daily life, as we'll dig in a little deeper throughout the talk. But I think reality would be a little bit different without technology. We've come to depend on technology for many, many aspects of daily life. And I think we would have a big surprise if we everything ceased. If you could imagine if the whole infrastructure for internet had dropped during this pandemic, what kind of shape we would be in. So I just want you to consider, you know, what happens during 1 minute in the internet. So an internet minute. So in 2017, you can just see the number of logins, to Facebook, the number of text messages, how many YouTubes we watch, etc. And we can actually there are many transactions that we can accomplish thanks to technology in just 1 minute. Eh, As we go the trend from 2017 to 2019, we can just see that this trend continues to accelerate and the numbers increase as we go through. So if you look at the 2020, it's really gonna trigger this because with COVID-19, it's changed everything that we do, and there's gonna be a substantial increase in a lot of these numbers. It has changed anything, as we do a lot of working from home, school from home, online, everything. How we manage our supply chain, how we get through everyday life. Years ago, in 2002, we launched G4, and people would ask, well, what is G4 going to do? Back then, we knew it was going to speed up communications. But if you think about, many of these companies did not even exist. A lot of applications, a lot of things have been created with the advent of this new communication technology. And I think G5 is going to be just as disruptive. So we're expecting a lot of things to come up in the near future. So let's review this concept that many of you may have heard about, the fourth industrial revolution. Of course, the first was with the introduction of steam engines. But ever since, with electricity, computing, cyber physical systems, we've really been changing the world in how we go about our business. Now, there's numbers that say that thanks to the fourth industrial revolution, that 65% of the children starting primary school today are going to be working in jobs that do not exist today. So this is uh, one of those interesting points that we should ponder about. But if we look at this last three trends, the uh, increase in how we use electricity, computing, cyber physical, this all have been enabled by semiconductor technology. So many times we take things for granted, and I hope that throughout this talk you will see the value and how a little device called the transistor has truly changed the world. It's an industry that has had tremendous growth. These are projections for the amounts of billions of dollars in the semiconductor industry, and we look. This is actual numbers, except for the last two are projections, but everything. So you can see just about everything from industrial, government, military, computer peripherals, automotive, just about every sector that is here. It's given the so we're over $2,000 billion a year that we enable through this industry. Of course, it has impacted society in many ways. Not only the economy, energy, health, healthcare, information, all the items that you can see here. We'll probably center in on some of energy, and of course we need to look at the impact that energy and energy consumption has had on the environment, how we've had it as an enabler for renewable sources of energy, thanks to technology and semiconductor technology in particular, and how we can mitigate in many cases environmental issues. So, of course, in the information area, it's information really is in the currency. So is generation, storage, transmission, and how we communicate. So it's whether we like it or not, it's a global economy, and we're seeing, some of the issues with this. Of course, it impacts how we interact with each other, and it's sometimes good, sometimes bad. It's changed the education, the political atmosphere, the entertainment. So you can just see many of the changes that have been brought about by technology. It's also in the public policy, and technology is well ahead of law in many cases. So there's no uh, rules and regulations. So we have to make some of those as we go along. Of course, a key area is that of ethics and professional responsibility for those of us, and I think everybody, not only that generate, but that use technology. And last but not least, we'll talk a little bit about humanitarian engineering and healthcare. Um, and all of this has been enabled by a little device called the transistor, which is nothing but a switch that can switch at very, very high frequencies. So here's the schematic for a typical transistor, where we have a gate, terminal, a drain, and a source. And we just modulate by putting a small voltage here. We can attract, if you put a positive, you can attract negative charges here, create a channel, and make the electrons, travel along this channel. As we make those channels smaller and smaller through scaling, we can just get the electrons to go faster, but we also get a gain in performance and energy. Uh, and this is the main reason why you get the newest electronics always come at a lower cost and more function. So it's all thanks to this transistor and scaling. And that's what has been enabling uh, the rapid pace that we've had. And in the gate terminal, we grow very thin layers of oxide. Most of the semiconductor devices are done in silicon, which is basically sand, silicon dioxide, and that's what we use for many generations. That's what we use now. We have introduced oxynitrides for very thin layers. 12 angstrom is 12 times 10 to the minus 10. So in 2018, we were about 12 angstrom, and the channel length was 14 nanometers. Latest technologies today are down to 7 nanometers in production. So this is Gordon Moore, one of the founders of Intel, just put this curve where he predicted that every 2 years we're going to have twice the number of transistors. And we've kept throughout this many years in the semiconductor industry roughly with this cadence. So now let's put this into perspective. In the real world, we can all visualize marbles, so these are about a millimeter scale. And then we start going down to a human hair is 100 microns, or 10 to the minus 6 meters. Cancer cells in the order of 10 microns, bacteria is in the order of a micron. Viruses, as we'll see, are in the order of zero point 0.1 or 100 nanometers, 10 to the minus 9. The last generation of transistors were at 14 nanometers. And if we look at a microprocessor, so we could fit 8,000 millions of transistors inside a leading edge microprocessor. And just think about that we could fit in the diameter of a human hair about 7,100 transistors. So you can just see the realm at which we're working in the nanotechnology and the semiconductor industry. So there's MEMS, other technologies that have been enabled. And as we're gonna see, at about this 20 nanometers, here comes somebody that is being very famous in this last few months, and has really upheld the world and completely changed, and I think substantially for the future. So it's about the 20 nanometer scale. So you can just see here where coronavirus ranks within the size. Um, Early days of technology, when I started working in semiconductors, we could make a full technology using about 7 elements. With 7 materials, we could just make a technology. A state-of-the-art, it's close to 50, and it's been a tour through the periodic table, finding the elements that give us the extra advantage. And the way we implement the transistors, the FETs, the field effect transistor, we've been using, and this is for CMOS. There's a different kind for those of you that know bipolar. So from the classic MOSFET to double gate, multiple gate, etc. So we've changed the structure to make them more efficient throughout the years. So you can see how we've accomplished that. So that has led to a significant evolution. If we look at what a computer was in 1960 to what it is today, we can see that we have a lot more power in the palm of our hands than NASA had for some of the early space launches. So we have achieved outstanding progress using semiconductor technology, and that industry has really been changing the world. Whereas there's other industries that have not really had the kind of advancement that we've had. If you look at the fossil fuel industry, there's been very little, progress. The only progress that has been brought about is in the measurement and the instrumentation that semiconductors provide to this industry. But basically, it's still doing the way things are. And this brings us to the carbon dioxide story in relation to energy and hydrocarbons. Now, it's a fact that our planet needs carbon dioxide to moderate climate. Without carbon dioxide, our temperature would be minus 25 degrees centigrade Celsius. And our planet has historically ranged between 180 part per million, of CO2 in our atmosphere during the ice ages, and it increases up to about 300 part per million during the interglacial warm-up periods. Now, we had a huge disruption, the first industrial revolution that I was showing earlier through steam engine, and was powered by coal. Um, and we will see the impact that it has had. And we now depend in the world on fossil fuels for a large share of our energy and transportation needs. And that has really changed the environment. So if we look at this as in thousands of years, uh, from 400,000 years ago, so we've had warm periods and cooler periods. So we can see that our planet normally oscillates between these ranges. But something very disruptive, so about 200,000 years ago, modern humans appeared on the face of the earth. And in just the last 200 years, with this industrial revolution, we've completely altered this balance and the cycles that we had throughout the earth. Earlier on, there was some people that would say, no, this is not man-made. I think pretty much is consensus. And every scientific paper in peer-reviewed journals, there are still a few papers that are sponsored by fossil fuel industry that still deny that this is a fact. But I think as engineers, we pretty much everybody in the scientific community, there's no doubt about it. And the problem with this, it has very strenuous consequences, if we keep down this path. Now, who are the main contributors to carbon dioxide? So here you can see by industry, and practices that we use in the generation of gas and oil. They tend to just burn the gases. Cement is a large producer. So generation of gas, oil, and coal. So if we do not develop cleaner sources of energy, we're going to have very, very dire consequences. So we're all concerned about this pandemic, but we'll get through that. This crisis, if we don't face the consequences, change our ways, the consequences are very dire. Something like extinction, and I think we would not be able to sustain life if we continue down this path. Now, it's a problem throughout the world. No, it doesn't matter. Here's the share for, say, I plotted for Latin America. It only produces 5.1% of the total emissions in the world. But nevertheless, every region, no matter wherever you are, we're all in one planet, and we're all going to pay the consequences, no matter where we are. The latest reading of CO2, if you recall, was at 380. Now, as of April this year, it's up to almost 418 parts per million. So the trend is not slowing down. So let's think for a second about what is the cost, the true cost of a gallon of gasoline. In the U.S., it's somewhere between $2 and $3.50. But my question to you is that the true cost of a gallon of gasoline? And the answer is obvious. It's nobody has been paying for this cost. There is the natural capital of our planet, and if we do not pay for it, our grandchildren are going to be paying for it. Unfortunately, corporations only pay attention to what's going to happen, next quarter, at most 10, 20 years down the road. But even large banks are beginning to pay attention and look at these issues. If we look at the temperatures on our planet, taking as a reference 1951, so this is a, a chart published by the New York Times from data from NASA. So you can just see that many, and particularly in the poles, we've been experiencing up to over 3 degrees centigrade, and this is a huge amount of change to heat up large regions in this. It's on a magnitude that had never been seen before. And we can see the consequences every day. You just have to take a look at the news, and you will see more and more of these stories. So it's the largest decade. Last year, was the second hottest year, and that even though the El Nino La Nina takes to moderate some of that. Antarctica, huge climate increases, and the results are uh, visible and palpable in all regions of the world. And the sad thing is that the technology already exists to reduce a lot of the emissions that we put out there. In the automotive industry, the electric cars are available now that can really, in many countries, have adopted standards, and they will be mandating that all cars are electric by 2030, 2040. So that is good. And we can actually generate a lot of this electricity that these cars will need, and that our energy needs, with means that are far more ecologically friendly. So we do not need the fossil fuels to generate the energy needs of the future. If we look at the transportation of an automobile, so it's really becoming more and more, so 60% of a car in 95 was mechanical. It's only going to be 35% in just 2025. Most of it is going to be software and electronics that are going to be. So it is something that is going to be enabled by semiconductor technology. And actually, with 5G, we're going to have autonomous vehicles and many, many other applications that are just already, being tested out. The next issue is water. So people are wondering if water is the new oil. If we look on the 20th century, most of the wars in the world were because of oil. And they claim, actually, as we head into this 21st century, it's going to be water that's going to be the most precious resource. But, so what is the big issue? Our planet is 70% covered by water, right? And we do need it to sustain life, right? But it's good to put the amount of water we have in perspective, right? So we are a sphere. So if we look in volume, This is the amount of water that we would have compared to our planet. All of a sudden, it starts to look like it's not quite as large, right? And 91% of that is salt water. So this is the smaller sphere here represents the fresh water. But over 90%, 99% is underground, very deep and not accessible to humans. This tiny little sphere here is all the water in the lakes, rivers, the surface water that we have been using and depending upon. And if we think about this water, through mining practices where we're putting heavy metals in our rivers, our lakes, with the advent of technologies such as fracking, we're contaminating a lot of this water. So some of this precious amount of water that we have easily accessible, we're damaging and taking it out of the consumption cycle. So our human body is close to, 72% of water. So we can see once again in a different way the amount of water that we have out of this small amount. This is it. So a different way to look at that. So technology is not going to solve every problem, but it's right now one of our best options, and through the use of semiconductor technology with the transistors that we have scaling and put more and more with solar sensors, we can make controllers, processors, cellular networks communicate. We can generate the instrumentation. And you've all probably heard about the Internet of Things, how everything is getting more and more interconnected as we evolve in technology. So I think transportation cars will be a reality in the near future. And it really is the forces of economy that always win. And so we need to be able to enable and optimize all the renewable energies and improve healthcare. And we need to collect better data to enable intelligent solutions, more efficient crops for in agriculture. So many applications. So the question is, how can we make a difference? And do you think that just one person can make a difference? I think it's a very good question. I just like to introduce you to Professor Jay Baliga from North Carolina State University. He was working in GE in the 1980s, and he perfected a type of tiny transistor called the insulated gate bipolar transistor. And thanks to this device, uh, everything and anything that has a motor has become far more efficient. So just about every modern appliance, any system, lighting from light, LED lights need one of these devices to bring the 110 down to the DC that are used by the either compact fluorescent light bulbs or LED light bulbs. So any electric car, airplanes, bullet trains, medical applications, they all have this device in common. So this tiny little transistor has enabled a plethora of applications and solutions. And if we put this in perspective, just by going away from electronic ignition systems in automobiles, in the US, it's saved 318 billion gallons a year, or around the world over 1477 billions, and that has resulted in this is terapounds, 10 to the 12th, 6 times 10 to the 12 pounds of carbon dioxide that we have not had to put in the atmosphere, and throughout the world over 28. So it's the same. Many of these applications have saved a huge amount. So we've eliminated over a trillion and a half gallons of gasoline. And so um, we did not have to construct close to 1,400 1 gigawatt coal-fired power plants at a great savings in money and carbon dioxide emissions. So it's interesting to see that one tiny little semiconductor device has already affected this much change in the world. We would be in far worse shape had we not had this advancement. For solar cells, they have completely, turned around. We are able to capture free energy from the sun, and the price of solar cells has decreased about by 80% since 2008. And if you look at the price reduction, nowadays you can actually generate electricity with a solar cell at a better price than you can with fossil fuels. So there's great hope, and eventually the economic forces will make solar cells the winner for uh, generation of electricity. So there's forces that want to, continue using fossil fuels because there's a lot of reserves, and that's how they develop the economy. But eventually, the forces of economics will prevail, and it's hopefully it'll be sooner rather than later, so we can do this before we have introduced more damage. For those of you that are electrical engineering students, I want to bring your attention to a new trend that is called thermoelectric devices. You've noticed how your cell phone heats up, how any appliance heats up, and we waste a lot of energy just through heat. So there's a practice, even way back in the Soviet Union in the 48s, they were already using. So you could actually, with the heat produced from a kerosene lamp, you could actually power up a radio. So basically, it's a way to have a generation of electricity by taking into account, so with a semiconductor structure, and we can look at the figure of merit, this Z. Uh, uh, um, Z-bar coefficient. So it's been increasing over the last few years. So we can just see that this is directly proportional here. So one of the ways we track in the industry is just look at the number of publications, and the steady growth in publications indicates that there's a lot of good research going on, and this is one of the fields that would bring about a, a very large change to how we use energy. So it's going to continue to be a key enabler for uh, renewable energy as we continue to go down. So it's not, you know, sufficient to just cross our fingers and wait for a miracle to happen. It really is up to us to make this happen. And how can we each contribute to doing this? And that's where groups such as SIGHT, and I'm going to show in the few slides some of the incentives and projects that we're funding to try to encourage this. So SIGHT, there's 138 groups in 48 countries. And in the latest number is over 10,000, getting closer to 11. And so there was 42 proposals awarded with over $300,000 in the last 3 years. And we've started to have joint projects within societies within IEEE. Last year, we funded $20,000 for a smart water irrigation project in Nicaragua, for instance. So you can see the growth of our membership throughout the years. And and this is the distribution by different regions of the world. This is the United States. Um, this would be Europe. This would be Latin America, and this would be Asia. So um, we're collaborating with different societies, with the Antenna and Propagation Society, Industrial Applications, Electron Devices, Microwave Theory, and beginning to fund more and more programs throughout the societies. Also working with EPICS and IEEE and with Eta Kappa Nu to make side activities accessible to these chapters. So we will continue to work also with the IEEE Foundation. So if we look at a typical, say, smart drip irrigation, we have solar panels, charge controllers, converters, microcontrollers, driver, solenoid valves, moisture sensors. A lot of this enabled by semiconductor technology. So we have actually started to fund through the Electron Devices Society. This is a fabricator in Mexico. It's capable of zero point 0.8 micron, which is very large in today's technology, but is the perfect size to make sensors and many of the applications that we need to fund some of these projects. So we funded 25,000 that was matched by the Mexican government, and we will continue to fund projects for SIGHT in the making of sensors for quality of water, etc. So here's an example of a pH sensor that was implemented, by integrated circuits created in this lab. So we have site groups, as indicated, throughout the world, very active groups of volunteers that are sharing their knowledge and the passion to help humanity in many of these projects in all regions. So our model is to have feet on the ground and have engagements that allow site groups to apply their skills to tackle the complex local challenges with the local communities, creating positive social impact. So there are calls for proposals, and you can just visit the site um, page in IEEE and learn about the many opportunities that are there available to fund some of these projects. So I just want to leave you with a few words on, a very relevant topic today is biosensors. So you can just have your pathogens, basically. And what we are using is semiconductor technology, so where we could add this into a device that we use as a detector, and then build the electronics, the amplifier, etc., to have a full electronics circuit, so that we can. So you saw a typical schematic of a transistor. So we can just, within our source and drain terminals, we can just change the charge depending on this solution, So we can integrate this biosensors with CMOS technology and create very inexpensive arrays to do that are portable. And this is an implementation by Jamal Dean from Canada on, what he calls a biological FET. So basically, it's you take advantage of hybridization, and you can make many detectors. You just put a drop of the sample solution, and then you can get the bonding on your molecules and detect through the electronics. So here's a different implementation using carbon nanotubes, where you can have these receptors and change the way we detect the signals. And this is basically how we've been able to do COVID-19 probes in 15, 45 minutes. And it's enabling what is called lab on a chip. So it's just using the existing know-how to be able to make solutions such as this. This is a lab on a chip you may have heard about. And it tests several, in this case, 8 parameters. A1C is an average of glucose for the last 3 months, creatinine, the glucose, many of this. In this unit, that's a startup in India, it's cost about $850, and each of the tests is less than $1. So it really changes the way of that we can detect and do at a very affordable price a lot of tests for, if you have early detection of kidney disease, you'll avoid a lot of people from having to go into dialysis. For pregnant women, anemia is and malnutrition are one of the signals that you could pick through this. So early detection in remote areas is very important. It'll save lives in more expensive treatments with early intervention. So they've teamed up with the government of India to make this. And this is going to be a webinar we'll have next month by Professor Navakanta. So I just want us to put things into perspective for where we have been, and just our planet is almost 5 billion years old. And let's wrap that up into a 24-hour analogy. So let's say this 4.7 billion years, we can make an analogy to a 24-hour day. So we'd start our planet at midnight, 12 midnight, and it takes 4 hours for the first microscopic organisms to appear. So in 5 more hours, to start having photosynthesis, which is the precursor to having an oxygen-rich atmosphere. So 3 more hours. So it's not until noon. So 12 hours in total until we started to have an atmosphere that was conducive to life. 6 p.m. is when sexual reproduction starts with microscopic organisms at the bottom of the oceans. And it's not until 10 p.m. that we get our first footprints on solid ground, on land. And then it takes until 11 p.m., so 23 hours until the dinosaurs made their entrance. And by 1140, they became extinct along with 75% of all the species on the planet in what was known as the fifth mass extinction. Then the next 20 minutes, we can see the race, how mammals came into the scene. And then it's not until the last minute that we saw the appearance of the first semi-human, roughly 3 million years ago. And if we go to the last 100 milliseconds, it contains all the recorded history of us as human beings. So just the last 100 milliseconds contains everything that has happened since we started to track. And in the last 5 milliseconds, we've actually introduced this exponential term called the Industrial Revolution. And it was brought about by technology, by improvements in technology. And we've seen what this exponential term has done to our planet. And it's something that we really need to make sure that we can track and ameliorate using technology. So we must be very responsible in how we use technology and leverage it to benefit humanity and our planet. And that pretty much is all I had for you today. So I'd like to thank you all for your attention, and thanks to Juliana for making the arrangements for this webinar. So with that, we can, take a few questions. Please feel free to access our website and IEEE SIGHT. You can just do a search, and then you can just actually uh, um, learn about the many opportunities to join and be a part of this change that we need to have take place in our world. Okay, once again, thank you. So I'll have Juliana read any questions if there are. If not, feel free to send them via email later on. And I think there's just a lot of opinions and a lot of things that we can all do um, as we move forward.
Yes, thank you, Fernando, so much for sharing this webinar and the content today. As Fernando mentioned, we can go ahead and save some of this rest of our time for questions. You can write your questions either in the chat box or in the specific question and answer area, and I will be looking at both and then passing along those questions to Dr. Godin.
Right.
So we do have one question, and this comes in from Niharika Gupta. How can people in industry help in your research?
Yeah, that actually is a very good question. And So obviously, in industry, we've kept uh, this amazing pace of improving technologies at a very, very fast rate. But I think recently, with this whole COVID-19, it has become uh, very apparent how important technology is for the detection. Nowadays, if we don't test, there's no way to end and go back to some kind of normalcy in our daily lives. So from the industry perspective, is it would be in particular in the semiconductor industry. I think a lot of the technology is available there, but it's to develop some of the applications. There are some very nice uh, applications that have come up as with the detection, for instance, people have put oxygen meters directly hooked up to a cell phone. So for those persons that are suffering from COVID-19, many times it's best not to go to the hospital unless your oxygen levels really drop. That means your lungs are beginning to fail. So that's one application that tells people, okay, it's time, to go to the hospital. And doctors monitor that, and they had a very good trial on that. But I think some of the most important ones is to apply the technology that is being developed nowadays with changing in our planet's temperature. Many communities around the world that depended on the melting from snow-capped mountains. The snow cover has disappeared from many of those. So their water resources are very, very scarce, and they're really hurting. So you can set up a drip irrigation system very inexpensively. You can just have, one of those Arduinos or Raspberry Pi to connect to sensors and make a very inexpensive drip irrigation system. So using the talents that you have as an engineer, there are many, many solutions that you can think of, and that we would be happy to sponsor with funds from IEEE SIGHT if you have those ideas. And in more specific ways, I think there should be more outreach from industry and working with universities. I think young people are very passionate about this, helping the environment and helping alleviate many of the problems that we have in the world. So I think even within whatever company you work with, try to create a side group internally and team up. You don't have to be an IEEE member to create to become a site member. And everybody, it's free to join. And then you can have access. You do need to team up with some, at least have one IEEE member and apply for funding. And that's one of the ways in which you can actually try to make a difference. So just sitting around complaining is not going to help anybody. I think as engineers, we all have the knowledge, and I think we have the responsibility to pitch in in whichever way we can. So hopefully we will see more and more applications. And with this Internet of Things that's coming up, and it's going to be faster, and the sensing that is going to be coming about, there are many, many opportunities that right now we cannot even think about. But I'm sure a lot of the bright young people coming up will be able to think through those. So I hope you get engaged and try to create a group within your colleagues in your industry, and then integrate to a larger picture of groups such as SITE or many other organizations that you could join and try to help.
Thank you. And now we do have a number of questions that have come in. One question that is somewhat related to the last one is, why do we still see a very poor collaboration between semiconductor industries and academia on these emerging applications?
there, you know, I I would not, completely agree that there's poor collaboration. There are several, active collaborations. Of course, industry is the main goal of, most large companies is, to produce, to make money. But yet, I think eh, they will, and everybody's finding out that is the more applications that are beneficial to humanity, the more revenue and new fields that you will be able to open up and create additional value. So yes, we sponsor most of the research that's um, sponsored is geared towards new applications or making the devices better. And I can speak mostly for semiconductor industry, right? So we uh, sponsor a lot of research, but yet that is going to bring about many tangible solutions. That for instance, as you enable 5G, the speed with which you will be able to collect and transmit data that would be very valuable for not only healthcare, for monitoring. Just think about the way we had to work just 10, 20 years ago. If we were monitoring a, a, a a tank of gasoline, you know, in an airport for airplane fuel, you had to go to the actual site and dip in a little spoon and take a sample in a little glass container, send it to a lab, and about a week, 2 weeks later, you could have a reading for that. Nowadays, you can put a sensor, and in real time, you can have those results. So I think, yes, there's room for improvement, and we should all seek to create projects and products that are going to be valuable and that will make a difference. But I think today, a lot of the way we can remain contained, connected, and interfacing, having webinars such as this, is thanks to the infrastructure that we have already built. The sad truth, though, is that there's a digital divide, and not everybody has fared the same, as well in these tough times. If your kid does not have a laptop, then he's not getting educated. And these are some of the solutions that we would like to bring uh, uh, solutions to communities. And that's one of the parts that we try to do through SIGHT. So yes, there is room for improvement, but it's up to all of us to try to make that difference. So that's the key message.
Wonderful. There has been a question about sharing the presentation afterwards, and I just wanted to let everyone know that this session has been recorded, and so the recording will be uploaded to the site website within the next couple of business days. We also usually share the presentation afterward in PDF format. And we do have another question in from Manoj. In what way should EDS contribute to combating COVID-19?
So that's a very good question. And actually, in 2 weeks, we're going to have a webinar by um, Navakanta Bhatt, one of our Board of Governors members. And he's actually going to be providing information on some of the sensors, some of the things that can be made. We are actually actively working with the leadership of EDS in particular, also to collaborate with groups such as SIGHT and fund. So we have a fast tracking for funding. If you have an idea for a detector, for a test that would be inexpensive and easily deployable to many communities throughout the world, we're funding those type of projects. So there's faster funding for some of those initiatives. So I think, and we're also having webinar series separate from site, with more in-depth discussion of some of the topics within Electron Devices Society as well. So I think there are many of these items that are taking place. And I think one of the major changes you're going to see is like conferences. A lot of our conferences have gone virtual, but it actually, there's opportunity there, because you can have, just as you will have access to this talk when you attend the virtual conference, you can view any lecture, for the following month, and we're looking for ways to make those accessible long after the conference has passed. So you can not only read the paper, but you can actually listen to the presenter, um, given their slides. So there's opportunities that we're looking at. So it's a good question, Manoj.
Okay, and now we've got a question from Martinez for you, Fernando. Okay, so it says humans need to migrate from fossil fuels to renewable energies, but in practice, renewable energy sometimes takes up a lot of places. And as we know, the world's population will increase, and this will mean more and more places are used to live. With this consideration in mind, should renewables still be used?
Yeah, I think there's no question we need to go to renewables. Yes, for instance, a solar farm is going to take a large area, that and we'll have to be careful about where we place those, so we don't take over agricultural land to do this. But yeah, yes, there's 7 billion people in the world and projected to grow to 9 billion, in just the next 20 years. And that trend is going to continue. Yet there's going to be another trend in society, in which people are migrating to larger cities. And nowadays, for the last, 30 years ago, I think was the turning point where more people live in urban centers than in the country. So I think there's plenty of space still, and it's not only solar cells. Just look at the eolic, wind power. We're also able to take motion of the waves to generate electricity. There's many ways that are clean, um, and that we can really make a difference and really, you know, stop depending on fossil fuels. And that is number one goal. So I think, yes, there will be challenges, but I've even seen solutions where they stagger the big arrays of solar cells within crops that can grow within the areas of panels. So I think it's just going to take innovation and good solutions. So I think, yes, it is a concern, but I think it's a solvable one. And I think the larger benefit uh, of the, you know, eh, ceasing to depend on fossil fuels, it's going to be well worth any minor inconvenience that may be brought about.
Great. Okay, so we've got another comment in just saying thank you, that it's great news for researchers, faculty members, the way that SIGHT and EDS are planning for the days ahead. Got another comment just saying thank you for your time, Fernando. And at this point in time, those are the only questions
Excellent.
or really comments that I see.
Yeah,
Go
thank
ahead.
you so much, Juliana. And I just want to close by encouraging everyone, even whether you're viewing this now or you're going to be viewing this presentation later on in a recording, to reach out and just do a search IEEE SIGHT, and you will be able to come up, with membership, with information about projects, how to apply for projects, etc. And I would strongly encourage each and everyone to be an active participant, and let's make a difference and use our education and resources um, to solve some of these major problems we have. Okay, thank you very much, and have a great day, everybody.
Wonderful. Thank you, Fernando, so much. We really appreciate the time you've taken to share this session with us today.